Hello, everyone. I hope everyone's been doing well. My name is Riley Fetty, and today I will be discussing the embodied mind and some dynamical approaches to cognitive science. A brief overview of what I'm going to be talking about includes the lexical and grammatical structure of language, minds of blind versus sighted language users, the A, not B error, embodied action, along with the roles of the body and the mind in abstract thoughts. So let's dive right in. In his article, Dynamical Approaches to Cognitive Science, Randall Beer goes over 3 models of dynamical systems and how they compare to more traditional symbolic and connectionist approaches. The 3 models of dynamical systems that he looks at are lexical and grammatical structure of language, Piaget's classic A, not B error, and active categorical perception in an embodied situated agent. Dynamical systems theories posits that cognition has evolved through time, allowing humans to understand more abstract concepts. The main motivation behind this theory is the fact that humans have evolved cognitively throughout our existence. So it seems that if cognition itself is dynamic and it can evolve with time. This approach is different from symbolic systems and connectionism, as it believes cognition can evolve, rather than cognition following a particular pattern. Symbolic systems and connectionism are used to explain many models of language, which dynamic theories agree with. However, they believe it is much more complex in many cases. We have evolved so much that we need dynamic systems on top of symbolic and connectionist models. So the first dynamical system that Beer looks at is the grammatical structure of language. So language is often seen as a strong argument for symbolic approaches to cognition. However, language understanding and production are basically temporal events with each word leading towards the next. This is why language works so well for dynamical modeling, as it can be used for a wide variety of different models, including models of the temporal structure of speech, perception, and production, abstract models of grammatical structure, and other models like a vector field. So in one experiment, Ellman used a backpropagation to train a simple recurrent network to predict words using a collection of 10,000 short sentences. The network had to learn the frequency of occurrence of certain words and understand the grammatical structure of language. After the training, a hierarchical cluster analysis was made, and it exhibited a major division into nouns and verbs, and then subdivisions of intransitive, transitive, sometimes transitive, animates, inanimates, etc. So when looking at language and its dynamical model, I couldn't help but to wonder if language is structured differently within those who are blind and those who are sighted. So to digress real quick, this next article that I found focuses on the role of hierarchical semantic relations and the dependence it may have on visual perception. In this study, 58 blind and 58 sighted language users were asked to give associations for a list of 75 Polish nouns. The mental lexicon is conceived as part of the memory store, which includes the language user's knowledge of the words. Elements of the lexicon, which are called lexical items, are organized in several ways on the basis of hierarchical relations. The 2 that this study focuses on are class inclusion and part whole. So class inclusion refers to the hierarchical structures of different levels of specificity. So an example would be that tree is a hyponym of the noun plant, and contrastingly, plant would be a hypernym of tree. While for the part-whole relation refers to many different types of part-whole relations, such as component-object, actor-event, portion-mass, etc. So using the tree example, branch is a meronym of the noun tree, and contrastingly, tree is a holonym of branch. So the question this study is asking is whether or not this kind of mental lexicon structure depends on visual appearance. And the results are pretty interesting. So as you can see here, 1,134 of the responses from blind participants were either hypernyms or hyponyms, which for the sighted, there was only 818. So blind participants showed a tendency to respond with more inclusive terms, specifically hypernyms, than sighted individuals. This gives evidence that the blind may rely on more class inclusion relations than those who can see. But in regards to the part-whole relation, there doesn't seem to be any statistical evidence differing the blind and the sighted. But overall, like those who are blind tend to use hierarchical relations when thinking about language, specifically the class inclusion. There are delays in language development in children that are born blind at a very young age, but by kindergarten, differences in language development disappear, sometimes with the blind showing an advantage over the sighted in certain linguistic abilities. I really just found this study to be fascinating, and I'm curious about a dynamical model that could be made to maybe captivate these findings. I think children can teach us a lot about cognitive development. So moving forward to Randall's Beer article still, he mentions Piaget's classic A not B error, which is a study for infants 7 to 12 months in age. For this task, an infant is placed in front of two similar opaque containers with lids. Initially, infants are trained to reach for a hidden object in container A after they observe it being hidden there. If the object is now hidden in container B, which is full view of the infant, and there is a short delay, majority of the infants will still attempt to retrieve the object from container A. So Piaget originally thought this error occurred because of an immature concept of object permanence in the infants. However, there are a couple of experimental studies that show this error may be sensitive to context, as infants were less likely to make the error if the two containers were made visually distinct, or if there was no delay between hiding and reaching, or if the thing that was being hidden was something of interest to the infant, maybe instead of a star, it's a cookie. If the infant changes its posture between A trials and the B trial, that also showed less likely to make the error. And then if they, instead of reaching towards the particular container, if they just simply looked at it, they noticed that they did not make this error as much. They would originally look at B. So in order to account for these observations, dynamical models are made using a generic dynamical theory of motor programming. The purpose of this model is to give the probability of reaching in a given direction. This action of reaching is directly connected to the cognitive processing happening within the brain. Although a dynamical approach can certainly stand alone, it is most powerful and distinctive when coupled with a situated, embodied perspective on cognition. So, in a dynamical approach to situated action, an agent's nervous system, its body, and its environment are viewed as coupled dynamical systems, as you can see right here. Given that bodies and nervous systems co-evolve with their environments, Beer believes it makes sense that there is a need for this tightly coupled perspective. From this perspective, the principal aim of situated agent is to take action appropriately regarding its circumstances and goals. Cognition is merely one resource among many in service of this objective. Three other important resources include physical properties of an agent's body, the structure of its immediate environment, and its social context. In this sense, Cognition can extend beyond an agent's brain to be distributed over a system of people and objects within the environment. A common example of this nowadays is how our cell phones are an extended part of our minds. Overall, dynamical approaches focus on engaging the body with the environment around us as to, coordinate patterns of behavior. This differs from computational approaches, which follows the sequential sense, think, act processing cycle. The way our body is involved in our cognition affects the way we think and perceive things around us. And I found this particular article, which looks into the roles of the body and mind in abstract thought. The results of these experiments suggest that it is not sensory motor spatial experiences per se that influences people's thinking about time, but rather people's representation of and thinking about their spatial experience. So for study number 1, 239 Stanford undergraduates were asked to fill out a one-page questionnaire that contained a spatial prime and an ambiguous question. The spatial prime was designed to get people thinking about themselves moving through space in an office chair or making an office chair come towards them through space. In both cases, participants were asked to imagine how they would maneuver the chair to the X and to draw an arrow indicating the path of motion. The left-right orientation of the diagrams was counterbalanced across subjects. So ego moving prime and time moving prime, there was equal amounts of both. The ambiguous question that was asked immediately after this spatial prime was, next Wednesday's meeting has been moved forward 2 days. What day is the meeting now that has been rescheduled? So the results were, as predicted, people used primed spatial information to think about time. So the subjects primed to think of objects coming towards them, like this, were more likely to think of time coming towards them. So 67% answered Monday and 33% answered Friday. Subjects who were primed to think of themselves moving through space, which is this one, showed the opposite pattern. Only 43% answered Monday and 57% answered Friday. So it does appear that people's thinking about time is indeed tied to their spatial thinking, which led them to do a couple more experiments on and around the campus. So for study number 2, they investigated the relationship between spatial experience and people's thinking about time. So they asked 70 people waiting in a lunch line the ambiguous question. So they first asked the ambiguous question, then they asked how long they felt they had waited in line, while also recording which quartile of the line they were in when interviewed. So this served as an objective measure of how much forward motion in line they had experienced, with people furthest along in line having experienced the most motion. So the results, as predicted, the further along in line people were, so the more forward spatial motion they'd experienced, the more likely they were to think of themselves as moving through time. Just to give a little bit more evidence, I'm going to go over one more study that they did. So study number 3, they interviewed 333 visitors to San Francisco International Airport. So they first asked the ambiguous question, and then asked whether they were waiting for someone to arrive, waiting to depart, or had just flown in. So the results, people who had just flown in were more likely to take ego-moving perspective on time. So 76% of them answered Friday, compared to those who hadn't flown yet, only 62%. So this set of findings suggests that just thinking about spatial motion is sufficient to change one's thoughts about time. It is incredible how the activity around you can affect the way you perceive time. I thought these studies were creative, and personally I couldn't have thought of them, which got me thinking more about how creativity is such a fascinating example of how abstract the mind can be and how it can be translated in so many different ways, including statistical studies like this, or, including artistic and musical acts. So in this article, it kind of focused on the phenomenon of creativity and how it's received a growing amount of attention from scholars working across a range of disciplines. While this research has produced many important insights, it has also traditionally tended to explore creativity in terms of the reception of products or outcomes, conceiving it as a cognitive process that is limited to the individual domain of the creative agent. Music involves such a wide range of sociocultural, bodily, technological, and temporal dimension, therefore leaving it perfect for studies for those interested in creativity in a more relational perspective. So in this article, they attempt to frame an approach to musical creativity based on a 4E understanding of cognition. So embodied, embedded, enacted, extended. They suggest that this approach may help us better understand creativity in terms of how interacting individuals in social groups bring forth worlds of meaning through shared embodied processes of dynamic interactivity. They also explore how dynamical systems theories may offer useful tools for research and theories that and is a theory that kind of closely aligns with the 4E perspective. In contrast with information processing approaches to mind, which tend to discuss cognitive processes in terms of internal computations and representations, the 4E perspective sees cognition as distributed across the entire body of a living system and its surrounded environment, and as continuous with the fundamental adaptive biological processes required for survival and flourishing. So creative activity entails at least the following 4 characteristics. The activity has an unpredictable outcome rather than a scripted known endpoint. There is moment-to-moment contingency. Each person's action depends on the action just before. The interactional effect of any given action can be changed by the subsequent actions of other participants. And the process is collaborative. So with all of this knowledge in my mind, I came up with an interesting experiment to maybe test creativity and perception. I would track the eye movements in teenagers from ages 13 to 19 throughout this whole experiment. And I would have them watch a professional drummer make a simple beat. I would then ask them to repeat the musical beat back. I would have them possibly do 2 more test trials, increasing the difficulties, but whether they are successful in repeating it or not is not the main focus of this study. After the repetition is over, I would ask the participant to come up with their own individual beat. And what I'd be looking for is I'm just curious to see if eye movements would be similar throughout each individual. And also when it comes to them making up their own beat, I'm curious if it would maybe be similar to the beats that they were originally given, or if maybe their eye movements correlated to the repetitive beats that they heard. Overall, dynamical models can give a lot of empirical evidence regarding cognition, but there's still a lot to be discovered about the embodied mind and cognition and cognitive science as a whole. So I'm really interested to see what other people do in the future. And here are my works cited. I really hope you enjoyed this presentation and hopefully learned something. Stay safe, everyone, and happy holidays.